Sine and cosine are omnipresent across various physical and quantum phenomena. Most of us are first introduced to these functions geometrically, drawing right triangles and measuring angles. But for advanced mathematical analysis, this geometric intuition is a trap. When we rely on drawn triangles to define our functions, we assume that concepts like arc length and angle measure are already perfectly formulated. At this stage in a rigorous proof, they are not. Instead of relying on shapes, we construct these functions from the groundwork of limits, infinite series, and the properties of real numbers. To see exactly how this is done, we turn to the framework established in Walter Rudin's classic text, Principles of Mathematical Analysis. Securing this non-geometric derivation is necessary before using these functions to model complex physical systems. We start by looking at the complex exponential function, e of z, which is defined by a universally convergent power series. Using this series, Rudin establishes purely algebraic definitions for two new functions, which he defines here as c of x and s of x. By adding and subtracting the complex exponential to its negative counterpart, c of x isolates the even part of the function, and s of x captures the odd. We can test this structure with a simple algebraic substitution. If we replace x with negative x, the structure of the equations flips the sign for s of x, while the sign remains unchanged for c of x. This gives us our first major identities. C of negative x equals c of x, and s of negative x equals negative s of x. We have successfully defined these core functions and proven their basic symmetry using purely algebraic operations. If we rearrange those initial definitions, Euler's formula natively falls out of the algebra. This yields a critical theorem. The absolute value of e of ix is exactly 1 for any real number x. The proof is straightforward algebra. Multiplying e to the ix by its complex conjugate collapses the series into c squared plus s squared equals 1. Notice the geometric implication. This equation maps a set of coordinates whose distance from the origin is always exactly 1. This shifts the perspective on the circle. It is no longer the definition of these functions, but a necessary output of their algebraic properties. The geometry of the unit circle naturally emerges from the properties of the complex plane. To understand how these functions behave dynamically, we need to find their rate of change using the properties of power series. Taking the derivative term by term reveals that the derivative of c is negative s, and the derivative of s is positive s. Think of a point moving continuously along our new circle. Its velocity vector points orthogonally to its position. Because the velocity is strictly orthogonal to the position, taking the derivative continuously rotates the values. Sine transforms into cosine, and cosine into negative sine. These locked-in differential equations act as the mathematical engine that generates perpetual oscillatory motion. Now we face the most critical challenge, proving using only algebra that these functions eventually curve back and hit 0. We start with our initial conditions. C of 0 is 1 and s of 0 is 0. Since the derivative of s is c, s begins to increase for positive values of x. If s increases, the derivative of c, which is negative s, becomes negative. This forces c to decrease from its starting value of 1. Rudin uses inequality 50 to show that if c never crosses 0, s must continue to increase. This leads to a contradiction. The integral of an increasing s would eventually have to exceed 2, which is the maximum possible range for the function c. Therefore, c must eventually reach 0. We can define the term x0 as the smallest positive number where this 0 crossing occurs. With this point established, we can define the constant pi purely based on this algebraic result. Plotting this mathematically, c of x curves downward and crosses the axis at x0. Pi is defined as exactly 2 times x0. Using this definition of pi, Theorem 8.7 locks the system together, proving that both functions exhibit perfect periodicity over the interval of 2 pi. We have rigorously discovered pi and proven perfect periodicity without ever measuring a physical angle. This rigorous construction provides the stability needed for more advanced applications. The immediate beneficiary of this rigor is the Fourier series, which relies on these functions to evaluate periodic data. Stacking these waves allows us to model complex systems, from digital signal processing to the behavior of quantum states. The trigonometric functions beautifully connect geometry, calculus, differential equations, and analysis, making them some of the most powerful and widely used functions in mathematics. To see more chapter-by-chapter mathematics content, please like, subscribe, turn on notifications, and share this video.